April 2020 semester ICT 6900 special topics in ICT Advanced Machine Learning কোর্সের lecture 10 এ সবাইকে আমন্ত্রণ জানাচ্ছি। Today's topic is anomaly detection, and this topic discuss to find out the anomaly of a point from some regular point or the good points. If there are different points in the plane which are detected as a good, already decided as a acceptable points, and a certain points you just want to test whether that point is within boundary of those given points. That means whether that is anomalous, that means anomaly to the other points or not. That is the point of discussion today, how to find out whether the point is within the given points or outside the given points. So this looks like very similar to the detection algorithm that we have learned earlier, but there is some special difference. We'll discuss on that. So let us discuss an example, which is the example of aircraft engine manufacture. While the engine is being manufactured, different quantities are collected. That means the test results of different quantities are collected, and they may be termed as X1 heat generated, X2 vibration intensity, etc. There could be 50, there could be 100 number of different features that you decide as a testing feature for the aircraft engine. So you collect all the data, and for each set of data you term vector called x1, x2 up to xm. So m number of examples, and each example has got n number of features. So let us take only two features, x1 heat generated and x2 vibration intensity, and you plot the data, and the data may lie over there by marked by red cross. Similarly, if you want to now test whether the new engine is within this data or outside the data, so you collect the features of that engine and you plot that point over there. The point is, if it is over there, that means within the data, the given data, then we call this is a okay. The engine may be termed as okay. But if the result falls over there, then you call that is anomalous. So when you find a particular engine which is not at par with the other data, then you may take the engine outside and do the rigorous testing, or maybe you do some servicing, and the result may lie again within the good data. Otherwise, the engine should be rejected. So there are more examples, but before we discuss more example, let us discuss on how to actually determine whether the point is within the given data or outside the given data. That means there must be some mathematical basis. For example, if you have a data set x1 up to xm and you want to test whether the x test, that means the features of the new engine, is anomalous or not. So the technique is you have to model all the x in a function called px. Px actually probability function. There are different kind of probability function, and we will use one probability function to model the different x's, given x's. And then what you'll do, you will just pass the test result, that means x test, the features of the new engine within that function, p of test, x test. And if this p of x test is less than a certain epsilon, then we flag that particular point. That means new probability, new test, x test. The probability of the new x test, if it is less than certain value, then we call flag or we call it anomaly. If it is more than epsilon, that means a set value, then we call it okay. So what actually we do, we set a probability, and within the probability, the data may be this one. That means if you set that boundary, probability boundary by this particular area, then all other points except that area is outside the boundary, and those points are anomalous with respect to those points. But since we have tested those points as a good point, then we may go further, we may increase the further boundary, otherwise we reduce the probability, set probability. Because the set probability for the outside point is less than the probability within the center point. Similarly, the boundary, if you increase further, that means if you reduce the probability, that could be your set value. That means you may treat the point's new point if it is within the last circle or last ellipse. Then you call that is a good point, and if it outside this boundary, that means outside the px, then we call it the anomalous. One example is this one, which is good one. Another example is this one, which is anomalous one. And this one is anomalous because this point is outside the boundary. That means it is less than a epsilon, a set epsilon. Now we shall discuss about a term called Gaussian distribution. Sometimes it is called also normal distribution. And this is a concept of statistics, and you are already familiar with this type of distribution. Then also I like to discuss this particular topics because this is the foundation of anomaly detection. So it is defined like this: say x is a real number if x is distributed Gaussian with mean mu and variance sigma square. So the distribution of the different point x with mean of those points mu and variance of those points sigma square, then a distribution, this type of distribution is called Gaussian distribution, and the symbol is x turtle n within bracket mu and sigma square. This is called script n, and this symbol stands for a certain equation or certain distribution of x with respect to mu and sigma square. Mu and sigma square are constant and x may be variable. So this symbol is termed as distributed as. So we'll read this line like this: x distributed as the normal distribution mu and sigma square with respect to mu and sigma square. So this is the diagram of normal distribution, and we also call this distribution as probability. And the term we use, probability of x parameterized by mu and sigma square. These are two constant and x is variable. So x colon mu comma sigma square, and this is nothing but this particular curve where the maximum point, occurs is called mu, and mu actually the mean of the x over the line, the distribution over the line, and then sigma is the width of the curve. This sigma is denoted as the width of the curve. So this p of x parameterized by mu and sigma square is defined by this equation: 1 over root over twice pi sigma exponential of minus x minus mu square by sigma square. So this is a particular type of distribution called Gaussian distribution or normal distribution. So mu is the mean because whatever may be the points given, you have to take the mean, and mu is that point, and sigma is the standard deviation. Some cases we call it sigma square, which is actually a variance, and sometimes we call sigma in place of sigma square, then sigma is actually standard deviation. The two terms are used interchangeably. So let us see some examples of that equation. If you have mu equal to 0 and sigma equal to 1, it means the width of the distribution is 1, and mu 0 means the mean value is at 0. This is the 0 point. So mean value is 0 and the width is 1. So, and the area under this curve is always 1. The distribution equation is like that. If you take integrate over the minus point to the plus point about the mean, and then you will get the area is always equal to 1. Then let us see the other case where mu equal to 0, so the mean is also 0, but sigma equal to 0.5. That means width is reduced. In this case, width was 1, now width is 0.5. But the tip has increased because the area is always 1. The area under this curve and area under this curve is also 1. So the maximum will increase where width is reduced and the center position remains same because mu equal to 0. Let us see another example where sigma equal to 2. It means it will be flatter. You see the tip has reduced but the width has increased because sigma equal to 2 and mu equal to 0 means its mean is at 0. But you see the other case where mu equal to 3 and sigma equal to 0.5, you can compare the two curves. In this case, mu equal to 3 and other previous cases mu equal to 0. So the mean point has shifted. It is not at 0. Now it is at 3. So width is 0.5, but the mean value has shifted. So these are the curve when mu and sigma are known. If you assume a value of mu and sigma, for example, and you can plot the distribution according to the previous curve. The curve was as shown previously, this equation. This equation, you put mu and sigma in the equation, and by varying x, you will get a bowl-shaped curve like this. So let us proceed and we talk about parameter estimation, because in our case the x will be given, all x will be given. We have to estimate the parameter mu and sigma square. So let us say these are the given point, that means x1, x2, x3 up to xn, and xi, all x is a real number, just a single feature variable. So these are the points and you can see the density. The density at the middle is highest and the density at the extreme points are lowest, for example. So this is actually a distribution of Gaussian distribution. If you fit x within this distribution, natural, the script n of mu and sigma square, then you will get a bowl-shaped distribution. But the problem is how to determine the mu and sigma square. Mu is defined by the average value over the x's. Xi summation taking into account of the sign of the x. All plus minus sign has to be summed together, where I varies from 1 to m and average over m, so you will get the mu. So average position of the curve you can determine by this equation. And the width of the curve, sigma square or sigma, can be determined from this formula. 1 over mu and I equal to 1 to m xi minus mu square. For example, this is 1x and mu is over there, the mean position. So the difference between these two positions, the mean and the actual point, and then take the square and sum all this together. So if there are points over, say for example, 1000 points, so for every point you will calculate the distance between that point from the mean position, and take the square. So you will get almost like how far the overall points is with respect to the mean position. So that is the width of the curve. So in some book or some application you will see 1 over m by m1. So it doesn't matter much because m is quite large. So in machine learning problem, normally people use 1 over m. So this is the curve. Once you know the mu and sigma, if you put that value into that previous equation, you will get the curve like bowl-shaped curve. Let us discuss about the algorithm for anomalous detection. And for anomalous detection, you have to calculate the density. You have to estimate the density of an unknown point. So let us elaborate how to calculate the density of a certain point in order to determine whether that point is anomalous or not. So let us assume that you have a m number of examples and x1 to xn, and each of x is the order of n. That means there are n number of features. So you have to first of all calculate the mean value for each features. Xj equal to 1 over m, I equal to 1 to m, xji. That means for each and every example you take xj means for example j equal to 2. So for each example you take x2 and then sum them together and get the average, you will get mu 2. Similarly, if you want to calculate the variance for that feature, then you have to follow this formula. The formula that we have already discussed. You can implement this equation by vector implementation. For example, the mu, which is consisting of mu1 up to mu n, can be calculated by this matrix equations. So if you have a test data like X test where the features are x1 up to xn, then what you have to do, you have to calculate the probability for each and every features. Say for example, you have to calculate the natural distribution of the x1 where with respect to mu1 and sigma 1 square. That we have calculated from that formula. Similarly, x2 will be described by this new n means your natural distribution, normal distribution, which is with respect to mu 2 and sigma 2. And we have already explained this symbol is nothing but the probability. So apply delta 2 sigma 2 in this equation, that will give you mu x2 p x2 mu 2 x2 square. So similarly x3 will be described by another function with respect to mu 3 and sigma 3 square. So the total probability of that test value will be the multiplication of each and every probability. So if you multiply them together, you will get the multiplication of all the probabilities and you will get the test probability, and that will be your summation of, it's not summation, it's the product of all the components. That means j varying from 1 to n, x probability of xj parameterized by mu j and delta j square. So let us summarize what we have already discussed and choose the features xj that you think might be indicative of anomalous detection. That means the choosing feature is important. For a certain problem, for example, the problem of finding the hackers in the web, what you have to do, you have to choose the features carefully so that that is representative for anomalous detection, and feed those parameters like mu1 up to mu1 and delta sigma 1 square up to sigma n square, and the formula is given by mu j and sigma j square. This is the formula that we have described in the earlier article. And for a given example, that means test example, compute the px. Px means probability of x, and that is given by the product of j varying from 1 to n. And if you elaborate the function is that one that we have already discussed. So if we put the subscript of j in every term, then you can have the different terms and then multiply them together. And finally, you decide whether it is anomaly case or not if the probability is less than certain set value, which is epsilon. So let us take an example to detect anomalous detection for multivariable problem. For example, these are the data for x1 and x2. There are two features. One is x1, other is x2. And let us say the the data corresponding the x1, the value x1, there is a mean value of 5 and sigma 1 equal to 2 and sigma 1 square equal to say 4 and sigma 2 square is equal to 1. So let us point out this point. Let us this point. Let us plot this point on this diagram. So this is your mu1 because this is equal to 5 and the width which is sigma 1 equal to 2. So this may be the width because you see the data is spread over from this point to that point. So that could be the sigma 1 and that could be the mu. Just an example. Similarly, if you mark the data of mu2 and sigma2, that could be the mu2 and similarly there would be on sigma2. So if you plot individual probability with respect to x1 and another probability with respect to x2, the mean value is 5 and width is wider than the other one. So your width is 2. In this case, width is 1 and the mean value is 3. So this will be a sharper case and this will be a flatter case. So if you multiply this together, you will get the total probability. So Px is nothing but the individual probability, multiplication of the individual probability, you get the Px. If you plot these two figures in a three-dimensional plane, one is x1, other x2. So if you vary this shape over x1 and x2, that will be a dome-like a three-dimensional figure. So let us say there is a test point over there. So this point is okay because it is within the other points. And if you mark this probability of this point in this figure, this may be that point, and that is more or less a high value because if you measure the height of this point, that is your px. Similarly, if you have another point which is out of this which is not in the close proximity of the given point, that is x2, and that is an anomaly case because that point corresponding px may be at that level. So this is a very high is not very high value. The height of this point may be very small. If you measure the p value from this curve or from this equation, you may get these figures. Let us say you have assumed the epsilon as 0.02 and we'll discuss this particular point how to decide the epsilon. Let us say we have decided this epsilon value following the standard technique. Then the p-test one, this particular point, may be 0.0426 and for this point it may be 0.0021. So this point is less than 0.02 and this point is greater than 0.02. In other words, this is greater than epsilon and this is less than epsilon. And that's why we call this point as an anomaly point. So this is the boundary line which encompasses the good points. So the outside point, that means the point outside this boundary, is an anomalous point. And this is evident from this probability function. If we find out the probability of this point, you will get the value is smaller than 0.02. That's why we call it the anomaly points. Somebody may get confused by comparing the analogous detection algorithm with the supervised learning algorithm. Because in the supervised learning algorithm, the results are given. That means the output level is known. And in case of anomaly detection, we also know the output. Of course, though we deal with only the negative output, that means the data is in the good shape, and we only find out the exceptions. That means when y equal to 1, that is the positive example, and that examples we want to detect from our anomalous probability fitting. So what is the actual application or where we should use anomaly detection and where we should use the supervised learning? So let us compare these two learning method. First of all, the anomaly detection, the various small number of positive examples. We deal with a small number of is ranging from 0 to 20, y equal to 1. That means, for example, in case of your manufacturing problem, whether the output is a problematic output, then we call it y equal to 1. So these are the very small numbers, but mostly we feed the probability function through large number of negative examples. That means the good cases. The cases where there is no problem, we take those cases and we feed the probability function, and later on we test the output of a certain test data, and if the data falls under the previous group, then we call it y equal to 0, and if it is outside this boundary, then we call it y equal to 1. So the number of examples, positive examples, is very small. But in case of supervised learning, large number of positive and negative examples. That means if you want to predict correctly the positive examples and negative examples, the training set should encompass all the possibilities of positive examples and negative examples. The other comparison point is many different types of anomalies may occur and hard for any algorithm to learn from positive examples. That means whether the particular type of anomaly will occur in the test case, you never can predict. Very hard to predict, and that's why it is very hard to encompass all the positive examples. That's why what the anomalies look like, future anomalies may look nothing like any of the anomalies examples we have seen so far. That means we may test 10 number of examples, and the type of those examples may be totally different for the future anomaly cases. That's why the concentration is only the positive cases where the boundary can be drawn, and the types of anomalies may be different, and that's why the anomaly cases are not taken into the training phase. But in case of supervised learning, enough positive examples for algorithm to get a sense of what positive examples are like. Future positive examples are likely to be similar to one of the training sets. That means the expectation is that you can encompass or you can predict all the positive examples and all types of positive examples really, and these positive examples you put under the training sets. If you see the example cases where the application is made. For example, in case of anomaly detection, the fraud detection is one of the examples. And normally, the fraud cases are very small, and normally the normal users are not involved in the fraud cases. So, if the number of fraud cases is less, then you can put in the anomaly detection. But if you see in your system, the fraud detection is as much as the non-fraud detection, non-fraud cases, then you should move this problem to the supervised learning. It depends on the how many type of or how many cases of fraud application is coming in the near future. The next example that we put in the anomaly detection is manufacturing cases. For example, aircraft engine manufacturing. And normally the aircraft engines would be good shape because all the design procedure has been followed. But in some cases, small cases, you will have the problematic aircraft engines. So that's why this falls under the anomaly detection. But if your manufacturing process is such there is a possibility of huge number of faulty engine, then you should take these cases or this particular problem in the supervised learning. Similarly, monitoring machine in a data set is the same principle you should apply whether you should keep into the anomaly detection or you should move into the supervised learning. In case of supervised learning, the examples are, for example, email spam classification, weather prediction, sunny, rainy, or etc., or cancer classification. And all the cases you have to remember that both positive example and negative examples should encompass all possibilities. It's not that a unknown possibility or unknown case totally unknown case which has not been which does not fall into the training set, then it is difficult to predict correctly. Selection of feature is very important for successful implementation of anomalous detection algorithm. In some cases, you will see the features, the distribution of the features is bowl shape. For example, if you plot the histogram of certain x, and this may look like a bowl shape histogram. Histogram means the number of data in certain band. So in the center position, the number of data is more than the data in the extreme positions. So this is a bowl shape histogram, but there are some features. Directly, if you apply the histogram, that may not be a bowl shape histogram. For example, this histogram is not a bowl shape histogram, it is inclined to one side. So in both cases, you apply the probability function or the normal distribution function, you will see the similar shape. Of course, it doesn't matter if the histogram is not bowl shape, but always it is better or it is convenient to visualize the output if the individual distribution is a bowl shape distribution. But in the latter case, for example, this is in this case you apply the logarithmic of the x, and if you apply then the histogram will be converted to the bowl shape. And if you see the shape, it fits almost like a Gaussian distribution. And this is a technique that instead of using x, you can use log x as the features. So x1 may be the original variable, log x is your converted variable, and use log x as your feature. And it could be log of x2 plus 1. Instead of x2, you may have to apply x2 plus 1 then log. And the generalized form is x2 plus c log of x2 plus c. In some cases, it is like root over of parameters. For example, x3 is the feature, and if you take the square root of x3, then the feature becomes almost bowl shape output. And this x3 to the power half, and the generalized form is x3 to the power 1 by p. So let us now discuss about the error analysis for anomaly detection. If you can analyze the error, then it is easy to, or it may have the opportunity to correct the error. So our objective is we want the probability of certain x to be large if it is a normal example. But if it is a case of a anomalous example, then you should expect a small value of probability. But the common problem is Px may be comparable, say both are large for normal and anomalous example. So if you know the output that one is normal case and other is an anomalous case, but the Px is comparable, so you cannot distinguish between the two. For example, these are the data set x1, the different data, and you can see the distribution is almost maybe bowl shape. And if you take an unknown, say this green point, and you see the value of probability is quite high. So you cannot decide that this x new x is a anomalous example. But if you can add another feature, for example x2, the distribution of the given points will be like this. And your x1, that means your new point, may be outside the boundary over there. So by adding a new feature, you can correctly predict or correctly determine whether the case is a normal case or anomalous case. So this is one technique that when your output is comparable, then you apply or you add some meaningful feature with your in your detection problem. So let us take an example of monitoring compute in a data center. We have discussed this problem before, Maybe we have four features. X1 is memory use of computer, X2 is the number of disk access per second, X3 may be CPU load, X4 may be network traffic. With these features, you may not be able to correctly identify the anomalous cases. But if you add some intelligent features out of these features, for example, X5 could be CPU load per network traffic. So that could be one new features. And if even that is not sufficient, you may add another feature, CPU's load square divided by network traffic. So by manipulating or by introducing more and more features, you may be able to detect or you may be able to determine the anomalous cases correctly. So feature detection or feature selection or the way of feature selection is very important in case of anomalous detection problems. If the number of features is more than one or the variable is more than one, then we determine the probability for individual features or individual variables and then we multiply them together to find out the combined effect. But there is a problem if we do the individual multiplication that we have discussed earlier, that the anomalous case may not be determined completely. So we may search for a method where the multivariable case, we can determine the anomalous detection very easily by a new technique. Let us discuss a motivating example why you want to search such new technique. For example, in case of monitoring machines in a data center, let us take two variables, CPU load and memory use. And the CPU load is almost proportional to the memory use, maybe depending on the different CPU, the memory use may vary slightly. And this data actually represents that kind of trend. If you take the average, then this average line is nothing but a proportionate line. Only the plot the value of x1 only, the points will be like this CPU load, and if we plot the memory use data, that will be like this diagram. So these two diagrams are almost Gaussian distribution. If you see the variation, the center concentration is more than the outskirt point. And let us see the given point in the two-dimensional plane. There is a boundary like a elliptical shape, and this is obvious because, as I say, mentioned that the two variables are almost proportional. So if I take a new example or new test case where it is marked by green line, then the x1 and x2 will be like this, like it will be close to zero point 0.5 and it is slightly more than 1.7 or something like this. So these 2 points, if I put in the two diagram, x1 diagram and x2 diagram, you will see the probability is not very low. That means it indicates that the multiplication may not be below the epsilon. So this problem, if I could make a combined method rather than the individual probability and then multiply, then the problem may be solved. So the new problem or the new method is defined by this way. The x is in the order of n because there are n number of features, and we do not model in this case px1, px2, etc. separately. Rather, we model px all in one go. And the parameters mu is again in the order of n. Each and every feature will have a mu, but a new variable is defined, which is covariance matrix, and this is a matrix of n by n. This is very similar to the matrix we have discussed in case of PC algorithm. And the formula that we don't have to remember, but the formula states that the P of x is parameterized by mu and sigma, and this equation is like this one: 1 over 2 pi to the power n by 2, and then absolute value of sigma to the power half, and then e to the power minus half x minus mu transpose, and then your sigma inverse, and then multiplied by again x minus mu. So this is your sigma, and that is determinant of sigma. This symbol means determinant of sigma, not absolute value, and this can be calculated by octave function called det. Det stands for determination. And if we see in the plot of this, your probability function that we already discussed for certain mu and certain sigma. For mu equal to 0, 0, that means it will be at the center, the highest point it will be center. And if sigma is 1, 1, it means both the dependency, there is no dependency between the two variables, so they're independent, and that's why the shape of the probability is a bowl shape. And if you plot the contour, you will see the circular, concentric circular points. At the center, the probability is high, and at the outer skirt, the probability is low. So if you manipulate the variable, for example, instead of 1, 1, if I put is 0.6, 0.6, like reducing the variance value, it becomes stiff, and the width becomes lower, like this one. If you see the contour, the circular radius becomes lower. The opposite case is if the sigma value is 2, 2, that means it is increased with respect to 1, then it is flatter, and the circle radius becomes wider. So let us see other effect, like in case of 1, 1 and 0, 0, if we discuss about 1 is 0.6, other is 1. That means in one direction covariance value is decreased, other direction does not decrease. So it will be like this one. X2 will be elongated, X1 will be normal. So this will be like elliptical. But this elliptical, the extension is the vertical side. The other option is instead of 0.6, if I increase to 2, then it will be in the opposite direction. That means the x direction, the ellipse will be larger diameter, and in the x1 direction, ellipse will be in the lower dimension. Let us see other variation. For example, if you compare with the original plot, if I decrease the other variable instead of the other one, the shape will be in this way. And the case of increasing one variable, not that both variables, it will be inclined in the other direction. So there are different possibility of actually encompassing your given data. So the given data, if it is elliptical in one angle, like the example that we have shown, it can easily fit by mu and sigma. So let us see the other example. For example, if we introduce the dependency, previously it was 0, 0, you see 0, 0. If we introduce dependency, then the angle will be different. It's not horizontal, not vertical. So it is angular. The axis is angular. Similarly, if I increase by 0.8, it will be again more in this direction, and it will be less in the other perpendicular direction. Let us see other effect. If it is minus 0.5, so the direction has changed. Instead of plus 45 degree, for example, it is the minus 45 degree. Similarly for point 8, again the same case, but it is in the opposite direction. The angle is in the negative direction. So what does it indicate? It indicates that in this method, the data encompass, that means where the data lies, the angular position and the plane, it can easily be simulated by these figures. In other words, we can easily get the mu and sigma value to represent the whole encompass or whole area of the given data, so that the anomalous point can be easily determined. Let us see other examples, like if I shift the mu, if the mu is shifted, only the center position will be shifted. So one is 1.5 minus zero point 0.5 or 0 to zero point 0.5. Its maximum probability point will be shifted. Let us summarize the algorithm for multivariate Gaussian distribution. So first of all, you have to calculate the probability of x parameterized by mu and sigma, and this equation that we have already discussed. So you have to calculate mu and sigma, and the mu is calculated by this formula and sigma is calculated by the another formula. Here the given training set is x1 up to xn, that means m number of example. Each of x has got n number of variable or n number of features, and if you sum all the features in one, all the vector, and for all examples, then you will get mu vector, and sigma matrix can be obtained from this particular matrix manipulation. And the method we can summarize now like this: fit model px by setting mu equal to this formula and sigma equal to this formula. This may be the sample data, that is example data, and then given new example x, you can calculate px and compare the px with an epsilon. If it is less than epsilon, then it is anomaly. So you don't have to calculate the px for individual variable, rather a combined px we can calculate from this formula. Although this formula is a bit computational expensive because there is a inverse of n by n matrix that causes a long time to compute. Otherwise, this method is convenient for use if in case of multivariate cases. So that's all for anomaly detection. Thank you.